usually works. And then I restart the share after that. Okay, we've got the recording going. We'll still wait until the actual minute. And just to double check, is the recording going? Let me double check one more time here. I don't want to miss the very first meeting. Oh, it says stop live stream. Yeah, so there's a little button that says streaming on YouTube that you'd be able to see on the actual Zoom client. So it looks like we're all set and ready to get going. Well, welcome back, folks. We're ready to start linear algebra. Our goal today is really to just kind of orient ourselves on the Moodle website, where most of everything in this class is going to happen is right here on Moodle. Then we'll also go with a really quick rundown of the syllabus right here. I imagine most people have taken a look at it, so we won't do a careful line-by-line reading, just look at the more important parts. And if we have time, we'll go to section 1.1. We may possibly finish it, but if we don't finish this section today for whichever reason, we will move the due date on this assignment 1 right here. Essentially, how the assignments are going to work is they're going to be on a section by section basis. So every assignment is just one section. And the day we finish that section, you'll have a 1-week turnaround for the due date. So if you finish it today, the due date is going to be the 18th. If you have to come back on Thursday to finish it, it will move over to the 23rd. Does that make sense to folks so far? Awesome. Well, let's go through the Moodle website, the syllabus as well, but maybe starting with the website itself. I'll be using this announcements form here for the first semester ever. I was notified by a colleague that that's actually pretty useful to folks. So any kind of announcements for the class, I'll put here, like the inclement weather announcements and such. Our syllabus will always be here. And if a revise happens, I'll always put a note right here to say the date it happened. And what the heck, we might as well just open that up. That's the next thing in the line. So here is the indication something got revised. And my revision's right here. I added a Tuesday for the office hours. And on these office hours here, I've mentioned you can come in through Zoom as well. So here's what the syllabus looks like. It's nothing too fancy, just a basic course layout here. I'm Mike Jacobson, and we're all aware that we're in CHE 215. But if inclement weather happens, like we mentioned before, you're always welcome to come in through Zoom. Other things on the syllabus is if you need to contact me, I'm available by that phone number there. And I'm usually more responsive on the email there. I'd say that's a better first point of contact. I'm almost constantly looking at that email unless I'm in class like right now. For office hours, it's going to be 4 to 5 p.m. That's going to be in my office or through Zoom. And on Thursdays, this one's going to be in the Math Center. The Math Center means it's going to be potentially a lot of different students there, but whoever shows up in the Math Center, we'll just go in a walk-in basis and the order people arrive. If you come in through Zoom, then you'll just be on the list as well as we rotate through the students in the Success Center. Any questions so far, folks, as we go through this? Yeah, go ahead.
Will these Zoom recordings be available for playback on Moodle or whatnot?
Yeah, absolutely. For every one of these Zoom recordings, you can go down to here on the recorded lectures. So this will turn into a playlist. Right now it's empty since we're just getting started, but they'll start propagating right here. I'll put the dates on them and the sections we covered, stuff like that. So it's easy to search through and get to where you need to get to. Other questions at the moment? Okay, so far on the syllabus, let's go down to the calculator policy. We'll mention a little bit more, but it's nothing major. Occasionally, it's kind of nice to have a calculator in linear algebra, but you'll notice I almost hardly ever use it, unless it's a very specific kind of problem. We'll see those in chapter 6. But just because it's a comfort, you can use a calculator during exams. It'll either be this one, TI-30X2S. That one's actually a pretty decent calculator for a lot of math classes. And this is the standard one you're probably already pretty fluent with, since that's used for a lot of courses like physics, chemistry, and so on. But those are the ones allowed on any exam. And so those would be good ones to use for your homework as well, just to make sure you're familiar with that calculator when you bring it to an exam setting. Any questions so far, folks, about the calculators or otherwise? Okay, let's keep on going through here. Next, well, we have prerequisites, the course description. I think let's go down to the homework we talked about a little bit. For the homework, it's very traditional in this class. So I'll post problem sets. You'll solve them either on paper, turn them in as a hard copy in class. But if you like working digitally, you can solve your homework problems just completely digitally and email me your assignments. I'd be completely fine with that as well. For the homework, you're all welcome to work in groups. And in fact, that's a really good thing to do. I encourage you all to work in groups. Only requirement is to write up your answers yourself instead of copying. And there's other good things we should mention here. Let's see. I put this as just a blanket statement on most of my syllabuses. So this statement here is probably less relevant for linear algebra. But it's just a statement for credit on homework. You have to show the step-by-step process, things like that. Well, let's go down to exams. We'll have 3 75-minute exams, a 2-hour final exam. The exams are going to be closed book, closed notes. But this shouldn't be too much of a bother since in linear algebra, it gets pretty almost like muscle memory how you solve these kind of problems. And whenever there's a big theorem that we have to use, I would put that theorem on the actual exam itself. So every exam is going to include a sheet of interesting theorems you might need and that kind of stuff. There's not a ton of memorization aside from that. There's other interesting things here, but we'll come back to those as we get closer and closer to real exams. Any questions about them so far?
So it's 3 exams of 7 classes, does it include midterm or?
Does not include a midterm, so we won't have an official midterm for this course. All the questions so far? Okay, then going down, this will be the breakdown of the class. And I think the important features are, for most classes at ISU, usually the final exam is anywhere between say 30, 35%. But for linear algebra, the homework is so vital just to get that extra practice on each one of the new problems. I bumped this up to 30% just to help kind of emphasize the need for getting lots of practice, lots of hands-on practice with these problems. If you're doing really well on this aspect of the course, then you're going to do fantastic on the exams. My exams are based off the homework. The homework is based off the lecture notes. And the final exam is kind of more of a formality more than anything. It will be based off the prior exams and the work we did after the 3rd exam. Well, that's how exams will go. And below is our schedule, but first, any questions about exams, the breakdown here?
I have a question, homework, since it's all gonna be on paper, do you have a craft paper that you need to work on, or just line papers fine?
Line paper's okay, yeah. I don't have any specific requirements. Yeah, that's a good question though, because I do know that some programs are very specific for what they kind of materials you can submit. But this class, I won't be too picky. So whichever you're most comfortable with, I'll be happy with as well. Other questions so far? Okay, and let me actually move this out. Trying to get used to, they increased the resolution of our projector so we can have more windows open. Just trying to find a way to really make that work for us. How about like that? I don't know if that's everyone in Zoom, but that's everyone who has, I think that might be everyone. Okay, so we have our Zoom folks on the left here. And let's keep on going down. This is our day-by-day schedule. And really the only thing that's firm on the schedule for sure is the exam dates. We already made an adjustment due to the inclement weather on Tuesday, but that's okay. There's a couple days of fluff built into the schedule, so we're not really losing anything. So we were meant to cover intro 1.1. At 1.1, we were possibly going to finish on Thursday. That's why we might bump the due date on the first assignment. I did make a note that this section right here, 4.1, is probably going to be the most infamous section of the whole course. It's highly abstract, and it's one where, as we get closer and closer to that section, it's a good one to take a preview of and start reading early. The more you can do any reading of this course, not just 4.1, the more it helps when you go to the actual lecture. That section is so abstract that if you come to the lecture with no preparation, it's a really tough one to fully grasp in real time during class. But despite that, we'll take 2 days just to get the extra practice. I don't think I have anything else super important to mention on the schedule, except for final exam will be Monday, April 29th. And well, I think you just about got it, folks. That's our syllabus. Kind of a fast run through. Any questions that folks would like to discuss so far? Okay, there's a lot more
Yeah,
stuff
I
on there.
actually do have one.
Go ahead.
So, like the last week of February, first week of March-ish, I want to say, yeah, the week of February 26th. I'm gonna be gone most that week.
Mhm.
Is it possible for me to just watch the class recordings and be fine?
Yeah, I'd say that would work out just fine. The class recordings are kind of convenient because you can pause it, play it back at 1.5 speed and all that fun stuff. I'd say you'd be okay doing 4.1 through the recording. And then if you had
Okay.
any questions as you're watching that recording, you can email me and I can give you clarifications.
Yeah, because I've got a trip planned that week and won't be in the state.
Well, at least we didn't put an exam on that date, so lucky on there.
Right?
Hmm. Any other questions about that so far? Okay. Well, we've got our syllabus ran through. There's more stuff here, but all this is just the resources from the university. Being an ISU student, you have lots of resources at your disposal. And there's more than just resources on here. For example, there is academic complaints and grievances. I would be very aware of this statement for any class that you take in the mathematics and statistics department. If things don't feel quite right, there's always people you can reach out to. Title IX is a super important statement about federal law and other things here, statement on services. So if you haven't seen these kinds of things before, I'd recommend reading through it very, very carefully. If you've seen a Title IX statement, then nothing's really changed about the law. But always good to go through these kinds of things just to make sure that nothing's missing and you're aware of all the resources. Any questions about any of these resources specifically? Okay, well, we did it, folks. That's, well, the read through of the syllabus. Still, we want to go through a couple more things. On the Moodle website itself, on the general tab is where we're going to collect a lot of just interesting resources, like, for example, calculators allowed on exams. That's just a pop out from the syllabus, but here's what they look like. This is what I would recommend for this class as a calculator. If you're really fluent with this one, then I'd say stick with it. It would do just fine in this class as well. Next thing here is the Zoom link. This is your one-stop shop for, say, office hours, or if you can't make it to the class because of road closures, things like that, you can come here. Like we mentioned, we're recording everything, and the class recordings will always end up right here. So if you need to go back to study, maybe you missed a class, that would be the place to go. And just to mention as a best practice, if anything looks missing here, then probably I just put the video in the wrong playlist. If you send me an email, hey, Mike, where is the lecture from Thursday? I'll get right on it and put it in the right spot. Sometimes it's easy to just get things mixed up with all the classes. After that, this one right here is something new that I'm trying out this semester. I'm not great with Discord. I just learned how to make a server just this Monday. But if you want to get help on homework, this would be a good place to go. If you want to form a study group with the class, with studying for exams, things like this would be a pretty helpful structure. And just to show how you can interact with it, let's open it up right now. If I recall how to get there. This cord, that should take me there. So this is what our server looks like. And I'm running it for all of my classes. So for linear algebra, you'd probably go down to this one right here. And I'm not great with Discord, but there's a lot of different things you can do to interact here. Say, for example, you're working on the very first homework assignment. As a student in this class, you're allowed to go to the actual assignment itself. Here's the problems. I don't think we assigned number 6, but let's put this on there anyway. One thing that's really helpful on a Windows machine, or really any machine, is the snipping tool helps quite a lot. And the shortcut to snip on a Windows machine is Windows, Shift, and S all at once. Your screen will go a little bit dark, and just grab, using this cursor, any element that you want to throw into the server. Let's grab that. You could paste it down here with a Control V, and you might write something like, anyone see how to start this problem? And that kicks off the Discord server. Really, this is expected that mainly students would be posting questions and helping each other out. But I'll try to come into the server and help out as well, checking it periodically throughout the week. So everyone's welcome to play around in here. study and help each other out. If you like, there's also a voice server. You can coordinate, screen share, and do all sorts of things as a study group through that as well. So if it works as an experiment, I'll try running it again. If you see a setting here that could be set up better, let me know and I'll try to make that happen. But keep in mind, this is just an experiment. It's a new way to get extra help on homework, but by no way is it required. If you hate Discord or if this just looks crazy, you're fine to completely ignore it. And you can always get help directly from office hours, sending me emails, things like that. Any questions at all, folks, about the Discord server itself? Okay, so that's what it looks like. It's kind of a weird place, but at least gives us a quick structure to form groups for the purpose of studying. Now, continuing through this website, we've got, after the Discord server, a couple bits of optional reading. So this is content about linear algebra, studying any math class, and things like that. And I'm going to get in the habit of putting all my Blink lecture notes in this file right here. They'll come in as a Word document and as a PDF. PDFs are far better for printing since there'll be a lot of equations right here. So you would need a good Word software to get that to print correctly sometimes. It can be really finicky. So the reason we have Blink lecture notes is because these documents here, after we solve them in class, we'll be uploading the solutions. So on a week-by-week basis, this is just going to be the work we did each day in class. You might not always go back to the video. Sometimes you're just looking for a problem right here that we actually solved. You just want to look at that problem. So that's how our Moodle is going to work. On a day-by-day basis, you'll always just go to the current week. You'll know what we're about to do. And for participating in the class, some people might just take ordinary lined notebook paper, write down the notes as you go. Some folks have found it's helpful to just take these and print them out. It's now like a worksheet, and you can fill in the worksheet as we work through the lecture. There's value in that, and you don't necessarily want to copy all this down by hand. It's already provided, and if you printed it out, it's all ready to go. And some folks might even just download these, work on them digitally. And that's what we're going to do when we solve these notes here. We'll just mark them up and save them. So that's pretty much the whole class. That's how it's going to work. The assignments will be posted right under the sections. And like we mentioned before, if we finish this section today, the due date will be exactly 1 week away. If we don't, that due date will get pushed out. Well, that's the whole rundown of the course so far, folks. Any questions, comments, concerns, or anything at all that folks would like to discuss? Yeah.
So you said that the filled lecture notes will also be posted, or just the empty ones to start with?
It'll start as an empty one, but once we solve it, we're going to post the solutions to them as we go throughout the course.
Oh, I see.
So solutions will go here, but if you ever want to go to the blank ones, sometimes it's helpful for studying. You'll always find them there. Other questions at the moment? How about over in the land of Zoom? Any questions so far, folks, at the moment?
None here.
Awesome, glad to hear that. Well, it looks like we're ready to begin, folks. We're going to sections 1.1, systems of linear equations, which makes sense. We're in linear algebra, so that ought to be our first definition. What do we mean by a system of linear equations? And before even talking about system of linear equations, we should just say what we mean by a linear equation. I mean, we could have great intuition on that, but that's a good starting point. We'll say a linear equation in the variables x1 through xn is an equation that could be written in this form. The feature is we have a coefficient multiplying a variable, so a1 times x1, added up with multiple terms equals some constant. If that's your format, you've got a linear equation. The values in front are the coefficients a1 through an, and they just have to be any real number, but they have to be constants. They can't be true variables themselves. So for our first example, all we'll do is take a look at these equations, determine if they're truly linear equations. And if they're not, we'll circle the part that made it nonlinear. Starting off with part A, how does that look to folks? Would you consider that to be linear or nonlinear? It turns out it's linear. It just looks weird, right? It's said here in this description, it's linear if it can be written in that form. So what we could do is just attempt to put it in that standard form in the definition. It'd be one operation, subtract x3 from both sides. And one more, let me fix my windows here. Still getting used to this new setup. There we go. We'll subtract x3 from both sides and get 4x1 minus 5x2 minus x3 equals 0. So we have the right format. The coefficients a1, a2, then a3 are 4, -5, -1. So we can say here, this one's linear. Well, that's one down. Any questions with that one, folks? Okay, going off to the next one, part B. How would folks feel about this one? Linear or nonlinear? Yeah, I agree. There's one huge problem with this one. The major feature about linear equation is that you have the variables separated by additions or minuses. You can't have the variables multiplying each other like in this setup. And so this portion right here, where word is kind of lagging, there it goes. Just that portion right there makes this, I said just, that's not the only portion, makes this nonlinear. Anyone see another portion that made it nonlinear as well? Exactly. One thing we cannot do to our variable is throw it inside a function like that. We can multiply it by a constant, but that's it. It can't go inside cosine, power e exponential, or anything like that. So, well, I guess we can circle just the cosine portion. This also makes it nonlinear. So if there was a plus inside here, and if we had maybe cosine 8 times x1, we would have been okay on this equation. That takes us down to part C. And looking at this one, we see a tangent 8, and that's weird as all heck, but you know, it's a constant, right? No different than 4. Likewise, we have a natural log 5 that's also constant. We have a -1 plus x4. So this one looks really weird, but sure enough, it is linear. So that's what our linear equations look like. Any questions about running through this initial example here, folks? Okay, once we have linear equations, we'll start studying the systems of linear equations. And in these notes, section 1.1, we're really just interested in when is there a solution? When is the system consistent? What does it look like when there's no solution? And how to find those actual solutions. Any questions at the moment? Oh, I shouldn't do that. Let me put this back together. Any questions at the moment, folks, before the next example? Fixing my pen here. Definitely don't want to break that right before class. Okay, let's go off to the next. And here's our bigger definition for this section. We'll say a system of linear equations is a collection of one or more equations involving the same variables. So here we have two equations involving x1, x2. This is automatically a system of equations. It's a simple one. There's two variables, two equations, so it's a 2x2 system in a certain sense. And we're going to try to solve it in two ways, graphically and then algebraically. Well, what we're looking for is a solution. A solution is a list of numbers. For us, it'll be a number S1, S2. So if you input those numbers in this equation, it checks as true. And same for this equation. So we're looking for a list of numbers to plug in x1 and x2 to make both equations simultaneously true. If we could do that, we found a solution. But what we want is all possible solutions, the solution set. They won't be too fancy here. It's either going to be a unique solution or no solution. But eventually, these will turn into really interesting overall sets. So that's what a system of equations looks like. And if we're going to solve this graphically, that's actually really hard. So I cheated a little bit and just plotted it out for us, so we don't have to try to draw that out. But essentially, this is how I plotted it. This axis here, we'd ordinarily call it an x-axis. Well, in this case, we're going to call it x1. It's a little bit odd. We don't have x's and y's because there could be many, many variables here in a system of equations. There could be thousands, for example, of different variables depending on what we're working on. So our next variable x2, we'll put it up here. And this equation right here got plotted to give this line, and this equation got plotted to give that line. We're looking for a set of numbers that makes them simultaneously true, but visually or graphically, it would be right here. That's our solution to the system. So we have a value 3 and a value 1. And we could say x1 is 3, x2 equals 1 is the solution. So nothing majorly fancy on this problem, just getting used to the definition was the major takeaway so far, and seeing them graphically. Any questions about them so far, folks? Okay, now when we're looking at these linear equations, the trouble with them is if we're working on, say, a higher dimensions, maybe it's not x1, x2, it could be x1, x2, x3, x4, and so on. These graphs are really kind of almost impossible to produce, less valuable at that certain sense. But when you see this graph, it gives us a sense of what's going to happen to a system of linear equations. There is always a trichotomy for a true system. A system of linear equations can either have no solutions whatsoever. That would happen if the plot, if it is just two variables, are parallel lines, never overlapping. There are three variables, they would be planes instead of lines. Those solutions mean you have parallel planes, they are never intersecting. So there could be no solution. There might be exactly one solution. That's what we're dealing with right here, exactly one. But what's a little bit odd about these systems are there'll never be two solutions exactly. You'll either have none, one like in this case, or infinitely many. So no system of linear equations has precisely two solutions, for an example. That's kind of interesting in a sense. But in this graph right here, it makes sense. You can make this look like it has two solutions if you make the curve do something like that, and this curve do something like that. Here's your next solution, but now it's not linear. We don't have a system of linear equations if your curves are doing this kind of behavior. So what we see here for the really simple system and the lines in the plane turns out to hold for every single system of linear equations. We're interested in when there's exactly one solution, but we're also interested in all the other cases when there's infinitely many, and having no solutions, that's very interesting on its own right as well. Well, if there is a solution, we'll call the system consistent. So in this problem right here, we can say this system. When we say this system, we're referring to that one up here by the red dot. This system is consistent. So consistency means you either had exactly one solution or infinitely many. And well, looks like we did it, folks. That's our second example. Maybe one additional thought. We specified how there could be no solutions. That is if the lines or planes are non-overlapping. But how would y'all say the system would look like if there were infinitely many solutions? Exactly. We have to have coincidence lines. Yeah, exactly, Quentin. So in other words, if you took, say, this line, maybe do something weird algebraically to it, double it. If this turned into x1 plus x2 equals 4, double this line, and you have 2x1 plus 2x2 equals 8. Well, that's the same line, right? Algebraically, they are really equivalent. Plot the top one or the bottom one, and now you have overlapping lines. And so for this setup here, this would have infinitely many solutions. Well, now that we have a feel for what this looks like graphically, let's solve this same system out algebraically next, just to get a feel for our methods coming up. First, any questions or comments at the moment? Okay, so obviously the graphical method is not great. You need software to make this happen. And if there were more variables, there's no great way to do this. You don't want to rotate a bunch of planes to see where they're intersecting. So eventually we're going to have to do this algebraically. And what I was thinking about on this one is, let's do what you might have done if you're not taking a linear algebra class. Maybe you're just in some algebra class and you're solving this system. We'll solve it algebraically, and simultaneously we'll use our methods using row reduction of an augmented matrix. So we'll see how to do it normally and our way on the rightmost column. But here's the analogy. If you think about long division, what that process looks like, say long division for polynomials, it's kind of a beast. It's not the funnest thing in the world, but you could always do this thing. Let's actually take a preview of that since it's just the first day. This is a very helpful analogy. I want to go to past courses. Let's go to this one right here. And I'm looking for 5.4, I think, division of polynomials. So that's the process that we all know and love. If you ever have to divide one polynomial, say this linear one, into that one, the quadratic, that's what the process looks like. It always works. It's just fine. But the more you do this, the more you're going to realize that everything that's done here, you could have done using synthetic division. Turns out it's only the coefficients that matter. Take 12, 10, and 3, throw them up there. Take this -2, make it positive. Do some weird number game, you get the right result, and you just divide using synthetic division. That's kind of the theme in linear algebra. You don't necessarily want to solve this using the ordinary algebraic method. You want to focus on the coefficients. It's only the coefficients that really matter in this system. And that's what the augmented matrix is specifically working on. So here, this is much like what you would have done in synthetic division for dividing polynomials. But let's do this again simultaneously. Let's take this system. We're doing the algebraic elimination method, so let's eliminate a variable. Notice that x2 has opposite coefficients. So if we take those equations, x1, so let me go to, yeah, this will be just fine. x1 plus x2 equals 4. x1 minus x2 equals 2. There's a lot of interesting things you can do to these equations. You could just add them up. This is not going to change the solution set. If you did that, in this column, you'll get 2x1. In this column, x2 is eliminated, and it'll be set equal to 6. So our new system of equations would be, let's keep the first row just the way it is, x1 plus x2 equals 4. And my second row, that equation, well, we use both of the equations, add them up. That's my new second row, 2x1 equals 6. So the system here looks an awful lot different than this system, but what is similar is they have the exact same solution set. We did not change anything fundamentally about the solutions when we did this right here. It is tedious, so at the same step, let's go over here and do row reduction of augmented matrix simultaneously. So this method says you only truly care about the coefficients of this system. We'll start by writing down a bracket to begin the matrix. On the first column, we're throwing in all coefficients of x1. Here, this is x1, really 1 times x1, so the coefficients are 1. On row 1, or excuse me, row 1 and row 2. We'll put in 1s there. And we move over to the next variable, x2. And the theme in linear algebra is pull coefficients. For the first row, it's a positive 1. And for the second row, coefficient will be -1. Now, when it says augmented matrix, what that means is we're involving the right-hand sides. And although this is not necessary every single time, it is a very helpful notation device to remind us we're dealing with the augmented matrix. Sometimes that is a very important reminder. So when I go to augment, I don't always do this on every step, but I start by putting this, and I'll end my reduction by putting in this right here. It captures the equality, and then we go to the right of it, bring in the 4 and the 2. So for you reread row 1, it's saying 1 times x1 plus 1 times x2 equals 4. On row 2, it says 1 times x1 minus 1 times x2 equals 2. So we just took the whole system, rewrote it slightly more compactly. Now, I want to get to that step next, and here's the idea. We're not writing out equality on this, so there's no equality on my next operation. What we're doing is something called row equivalence. So we write this little symbol, tilde. Let's write here just for emphasis. This is the row equivalence. Let me try to spell equivalence first. Equivalence operator The next matrix we're putting in is not equal, but it'll be row equivalent, meaning the solution set from this system is not going to change. And here's what we're going to do. I want to eliminate that right there, so we can take row 2. I'll put in uppercase R2 to refer to this row 2, and we're going to swap it for something new. Right arrow means we're making a change of it. Row 2 is going to be replaced with, you can think of that right arrow saying, we're going to replace it with itself plus row 1. So R2 plus R1. Let's write that out. Now my only changes in row 2, I'm going to just start by copying in row 1, 1, 1, 4. Because this is a middle step, I won't put the dots in the middle here. I'll just try to put that in the next step. If you like, you can put it in right now, but I feel like it becomes tedious doing it each and every time. So now row 2 is replaced with row 2 plus row 1. That means we're just adding these up. So here, in that column, that'll sum to a 2. We'll throw it in. This column will sum to a 0. And this column will sum to a 6. So that's our first step, algebraically, and using row reduction on the right. And when you look at this, we have this and this to compare against. Coefficients go 1, 1, 4. So we see a 1, 1, 4 as it should be. Next, take a look at the row 2. Our coefficients go 2 plus 0 times x2. There's really a 0 there, even if we don't write it in, and 6. So 2, 0, 6. And that's what we have right here. So our row reductions is just a way to not have to write down all of this stuff each and every time we solve a system, because all that truly matters is those coefficients. Do a good number game on the coefficients, and you're doing ordinary algebra. Again, just like with this strange synthetic division, replacing long division right here. Well, let's go off to our next step. We're just about ready to solve this system. We have, say, divide 2 to here and here, and x1 is 3. We already have a solution. Let's make that happen. I'm going to copy down row 1, or equation 1, x1 plus x2 equals 4. On equation 2, you can divide that whole equation by 2, and you'll get x1 equals 3. So we're halfway there for our solution. Now let's do it on the right. On the right-hand side, well, if the operation of dividing by 2 makes sense here, you can do it here as well. And it turns out that is absolutely allowed. Here's what it would look like. We'll write that this old matrix is now row equivalent to something else. We're not changing row 1, so we won't say anything about it, but we're changing row 2. So I'll write here in orange, R2 gets, we're dividing row 2 by 2, so 1/2 times row 2. So here's the new augmented matrix, 1, 1, 4 to start for row 1. And then we divide row 2 by 2, we get a 1, 0, 3. Let me try to fix that 3. So we're getting there, folks. Again, if you look at this row, it's 1, 0, 3 matching with this, and this is still a 1, 1, 4. All we now need to do is solve for x2. Any questions at this stage so far? Okay, well, let's see. If we're solving for this x2 right here, one thing you can do is multiply this equation by -1. Let's write out a new equation to show that. So I'll copy equation 1, x1 plus x2 is 4. Let's multiply equation 2 by -1. So it'll be -x1 equals -3. Now we have two equations, same exact solution set as the very originals right up above. But now we can tally these. x1 has been eliminated, x2 copies in. And the right-hand side here, it combines to a 1. So x2 equals 1 on this one. So just to double check, let me highlight these. We found x1 is 3, x2 is 1, and those were the right solutions when we did it algebraically as well. All we have to do over here on the right is show what that would look like in an augmented matrix. Let's see if I can zoom out without it being too small. Is that still decently readable to folks in class and over Zoom? Awesome. That gives me a good, I probably wouldn't zoom out any further than this typically. So here's our next step. I want to do this in 2 stages, kind of how we did here. So let's multiply row 2 by -1 to get a negative put in here, and then we'll add it to the entries above. The way that could be written in is last matrix, row equivalent to doing the following. This time we are changing row 1. We want to eliminate that one above, so we'll write row 1 gets replaced with row 1 minus row 2. It definitely looks funny, but that's what we were doing over here when we got to this line here and tally. So let's put that in. So here we're changing row 1. That means no change on this. Let's copying row 2 to start, 103. It's a good time to recall we have augmented matrix. We're just about at the end, so I'll put that in as a reminder. Now, this says row 1 minus row 2. So visualize this part, negative row 2, as a -1 is multiplied here. So now it's -1. Being added up to row 1 gives you a 0. Then it just happens all over again. You multiply by -1 here, no change. Add it to this entry, and it stays as a +1. Multiply this entry by -1, add it to the entry above, and you'll get a +1. We got it, folks. This is the system that we were trying to get to. And if we bring back the original symbols, x1, x2, here it goes, x1. Let me see if I can fit that a little bit better. x1 for this column, x2 for this column. And then just read out the rows. Here's what the rows say. 0 times x1 plus 1 times x2 equals 1. Let's skip the 0 and just write out row 1 by saying x2 equals 1 is what that first row is saying. Row 2 is saying, well, this 1 is relative to x1. So 1 times x1 plus 0 times x2 is equal to 3. Or definitely better to just say x1 equals 3. So somehow, some way, this weird number game that we did over here is all you really need to get the same exact solution, 1, 3. Any questions, folks, on that last step there? Yeah.
One question is, so when it comes to the manipulation of the matrix, like for example, first in R2 plus R1, and then we add R2 on the next step.
Yeah.
Is that the system that you do every time, or is this just only by intuition for this individual equation?
Yeah, it's because of this specific equation. Yeah. Row reduction turns into a very, very interesting number game. And the method that you'd want to take is a new ad hoc approach for every new matrix. But there is some guiding principles, and those are the elementary row operations. These are the things that you can do on any system. So our goal is try to produce a lot of zeros inside your matrix, so you reveal the actual values of each of the variables. And the way we do it is those 3 things there. But yeah, this system itself, a different student might have taken a whole different approach, maybe more, maybe less steps, and got the same exact answer. So there's a lot of ways to navigate through each and every one of these row reductions. Well, other questions about that so far? Okay, well, let's keep on going. The elementary row operations that we took were replacement. This one's a very, very powerful row operation. It says you can replace one row by the sum of itself and a multiple of another row. Let's read through that carefully. We did that here, and we also did that here. We replaced one row by the sum of itself and a multiple, 1 times row 1, of another row. Here, we replace row 1 by itself, plus the sum of a multiple, -1 times another row, row 2. So that's the row operation that is very, very powerful. We never used this one. It says you can interchange 2 rows. That definitely seems plausible because if you interchange these 2 rows, you're just interchanging the 2 equations. That is in no way changing the solution set, which equation you wrote first. So if it's valuable, you can interchange rows. We'll definitely do that on these notes. And the last one is scaling. Sometimes you want to rescale something. We did that right here. We rescaled row 2 by a half because it was convenient to make this 206 become a 103 to solve the system. So that's the rescaling step right there. As long as you're doing these 3 operations, you're in good shape. Now we're not making matrices that are equal here. All of these matrices are unequal as algebraic objects. And so that's why we're using the row equivalent symbol. That's the tilde right here with A row equivalent to B. And just as a reminder of its importance, forgot where I was. Let me go back to forgot my thought. Just as a reminder of the importance of row equivalence, I put this here as an assignment as well. Be sure to not use equality. We need to use row equivalent symbol, the tilde, when we're using row operations. So that symbol there. Well, let's give this another try. It says here as a theorem, the augmented matrices of 2 systems that are row equivalent have the same solution set. So just like we did above, making row equivalent systems didn't change the solutions at all. We got 1, 3, either way we did it. Any questions at all, folks, before we try out our example 4 next? Okay, so example 4, I put this in red right here since I did forget to include this in the original notes. We also want to solve this system as well. I put this as the first step, not because it's required, but it's always probably one of the more important skills in linear algebra. If you have a system, you should know what the equations are. And if you're given the actual augmented matrix, you should be able to write that out as well. I think I said that in a weird way. Let me try again. If you're given a system of equations, we need to produce the augmented matrix. But we also have to be able to go backwards from the augmented matrix to the system of equations. So the fact that this one has been augmented is definitely a really big deal right there. It means it's not a bad idea to take. I put a little dash line here because this is where your equality is going to be. Next thing you might want to put in is x1, x2, x3. That's pretty good as starting out, just as a reminder, but I think folks stop doing this the more you do these row reductions. And just as a reminder, or not reminder, but just as the indicator of this orange color, on my notes, I use orange to say this is just extra information. It's stuff that I'm going to use a lot, not necessarily all the course, but for example, even this right here, you don't have to put on your homework assignment unless it's helpful. So let's go and write out the system. Any volunteers for what the first equation should be? Yeah, go ahead.
1, 2, and 2,
Exactly. So that's pretty much the major thing to take away from our first day today. If you can go from the row 1 to equation 1, you're in great shape. Let's write out the rest of them just for the sake of completing that step. So row 2 goes 2, 5, 1. So it's 2x1 plus 5x2 plus x3 equals 9 as well. And for row 3, it goes 1, 3, 4. So x1 plus 3x2 plus 4x3 is -2. So there it is. That's the original system of equations captured by that augmented matrix. All the augmented matrix gives us is all of the coefficients of that. And we can definitely solve this system purely algebraically using ordinary methods if we wanted to, but that is a terribly tedious slog to try to solve that by hand without augmented matrices. So what it says here, then solve this system, we're going to stick with this still. We're going to row reduce that system there. Any questions, folks, before we begin with this one? Okay. Let me see here. Let's scroll down just a bit. And let me see if I can paste that in. Oh, let's maybe go this way. That might work a little bit better. We'll use an arrow. So first step, we're going to say we have row equivalents to a new matrix. And here's the number game that we're going to start to play for this system. First thing I look at is the farthest left upper entry, that one right there. We're going to later call that a pivot position. And what we want is everything below it to be eliminated. We want to get zeros down below that one right here. That means row one is not going to change. Let's start by writing in row one. It's 1, 2, -2, 9. And now we're going to start using the row operations. So we need to eliminate the 2 right there by the red dot. Since that's in row 2, we'll write row 2 is replaced with row 2 and multiply something by row 1, add it to row 2 to eliminate that 2. Looks like the value ought to be -2 on this one. So -2 times row 1 is going to be added to row 2. So again, if you write this in your homework, that's a pretty good help, I'd say, but it's completely optional. You don't have to write this in. So here's what it's going to look like. First, focus on the -2 times row 1. One thing that you could do to start out is just write it out. -2 times row 1 goes -2, -4, 4, -18. So that's our -2 times row 1. It says below, we're going to be adding that to row 2. So let me put row 2 under it, 2, 5, 1, 9. Tally those up, and we're getting a 0, 1, 5, -9. So this is not a bad strategy, writing it out here on the margin, but the downside is that could be a fantastic amount of writing if we did this every single time. Really, we're putting it here just for emphasis. This is what it looks like. And what we really write in is just 0, 1, 5, -9 right here. But if it helps starting off this process and just seeing what's happening mechanically, no harm doing this to starting out on assignment 1. Does that make sense to everyone on getting that row 2 so far? Okay, let's try this out again. And instead of doing this kind of tally work on the right, let's try doing it directly. Let me know if this is confusing. We'll go try it again as well. So we're going to replace that 1 that's right here. We would rather that's a 0 if we're solving the system. So that means we're going to write R3 gets replaced with. We're replacing it with itself and something times row 1 where it's circled there. Here we just need to take a -1 times that, add it to the entry below, and we get a 0. So we'll just say -R1. We're multiplying all of R1, row 1, by -1, in other words. So here's what people do in practice after doing this for a little bit. We focus here where it says -R1, then by the red dot, that's now a -1, multiplies this below, gives a 0. Then rinse and repeat. This is also multiplied by -1, so it's now -2. Take -2, add to the 3, and we're now at a 1. Then rinse and repeat. We just keep on going. Might remind yourselves we're multiplying by -1. So this is a +2 now after multiplication. +2 plus 4 takes us to a 6. And then one more time. That'll be -9 added to the -2, and we get a -11. And this is our new matrix. Does that make sense, folks, on how that process goes? Awesome. Like I mentioned, there's no harm in doing this, but after a while, with the amount of row reduction we're doing, this is a significant amount of time to write that out each and every time. I'd encourage folks doing it mentally like this is a good way to go. So our goal is to take this entry, which we call the pivot, and get zeros below. Now, after we have zeros all below, you move down and right until you hit the next non-zero entry right here. That's our next pivot position, and we want to eliminate the entries above and below on this thing. So let's make that happen. And before we get too far ahead, let me put in this important note. It asks us to solve the system, And because of those instructions there, this is the only reason why we must eliminate entries above and below the pivots. So if we're solving the system, we're going above and below at the same time. The next question is going to ask, is it consistent or inconsistent? And that's a slightly different process. And it saves a great deal of time spotting the difference. So I'll try to make a note on the next problem as well. Let's give this a try. We have a couple operations on this one. We'll write row equivalents again. And the only thing that's not changing is row 2 this time. So let's start by writing in row 2. 0, 1, 5, -9. Okay, now we're going to make our changes. Let's start by eliminate this 2 right here. That means we're affecting row 1. Row 1 is replaced by row 1, and we're doing something to row 2 below it. Anyone see what we should multiply row 2 by? Exactly, multiply it by -2, add it to the row above, and you've wiped that out. So it's row 1 minus 2, row 2. Let's make it happen. Now, one thing to notice is, because of that 0, it didn't matter what you multiplied. Multiply by -2 or 1,000,000, add it to the row above, and it's still just a 1. Likewise, it's always going to be a 0 down below. The changes start at column 2 going next. So here's the number game. This is a -2, add to the entry above, so 0. Multiply this by -2, we're at -10, minus 2, so we're at -12. This one's multiplied by -2, so we're at 18, plus 9 for a 27. So I think we've got it. Does those numbers look all right to folks so far? Okay, we do loads and loads of arithmetic like this, but we get pretty fast at arithmetic after a while doing all this linear algebra. So that's one nice side benefit of this course. Now we have to do the same thing all over again, but affecting row 3. This one's not so bad. You can take row 3, replace it with row 3 minus row 2. When I wrote minus row 2, my thought is multiply row 2 by -1, add to the entry below. That definitely wipes this out and makes it a 0. So let's keep on going. That's a -5, add to the 6, giving a +1. Multiply by -1, we're now +9 minus 11 for a -2. So for this pivot position, we're in great shape. 0's below and above, but there's nothing above, so that's technically true, vacuously. Here, on the next pivot position, we have 0's above and below, so we're in good shape. And we go down 1, right 1. That's our remaining pivot position. We don't worry about anything below it, but we need to eliminate all the entries above now. Once we do that, we'll have our solution. Yeah, go ahead.
I was just curious, there's specifically why we always down one for solving these.
Oh yeah, because essentially what we're doing is, if we eliminate all the entries down below, we have to move over to the next variable to get that next eliminations. So in other words, right here already, we have a solution that x3 is -2. That's where eliminate the entries right here. So we can say x2 is something. And likewise, once this is eliminated, we'll be able to say x1 itself is something else. So that's the reason for trying to get it in a staircase pattern with those pivot positions. Does that make sense with that question there?
There's just middle line to upright, or there's just a pattern thing, just easy.
Yeah, in fact, this pattern is so common that in section 2.2, we're going to call it echelon form. Echelon, German word for saying a staircase type shape. So it's always going to be kind of like this. You might have to move right several spots if there's lots of zeros and that kind of stuff. But yeah, it's always going to take that type of shape. Other questions at the moment? Okay, well, a couple operations on this one. We have to eliminate the 5 and the -12. But it's really not too different from what we've been doing so far. First thing we can say for sure is row 3 is just fine the way it is. So let's copy it in. 0, 0, 1, -2. because this is going to be our last step, this is when I typically bring back the dots to say this was an augmented system. So I'll put it right here. I put an orange here to say it is optional. You don't have to do it, but it's a very helpful reminder sometimes. Now, here's our next steps. We have to get rid of that 5. So we'll say row 2 replaced with row 2 minus 5, row 3. So this is saying take -5 times row 3, so that'd be a -5. Add it to row 2, we'll get a 0 right there. So this will turn into, well, first, before we do all that, notice that because of these zeros, I'm multiplying all this by -5, adding it above, but there's no change here, nor here. In fact, this is going to be 0, 1, 1, 0. The only possible changes occur right here, where the non-zero entries begin. So we'll multiply by -5 here, add it above. That's a 0. Multiply by -5 here for a positive 10, add it to the entry above, and we get a 1 right there. Last thing to eliminate is the 12. But effectively, you're just multiplying 12 on row 3, adding to the entries above. If you like the notation here, then you could write row 1 replaced with row 1 minus 12, row 3. If this notation looks like it's more of a bother, you don't have to use it. It's purely optional, and I'll probably stop using it after we're past chapter 1. This is more getting started, and it's kind of a paper trail of what we actually did on each step. But you'll notice it's, again, just a weird number game. Take -12 times this, add to the entry above, and you get a 0. But you have to copy that step. Take -12 times this, it's a positive 24. Yeah, I'm starting to see a problem there. -12 plus of this, and this is -24. That's not 0 at all. Let's try again on that. Thanks for spotting that, folks. So I put a negative right here. That should be a positive right in that location. So positive 12 times -12, yeah, that gives the 0. That's correct now at that stage. Now positive 12 times -2, that's a -24, plus 27 takes us to a 3. That looks a lot more correct. The numbers could get big, but these problems that we're doing in our book, they're kind of rigged problems where the numbers are nice, so you can do them by hand, focusing on the concepts, not the nitty-gritty arithmetic. So if a number turns into like 10,000 or a crazy fraction, probably there's some weird mistake like that one there. Well, at this stage, recall we're trying to say what the solution is. So much like we wrote x1, x2, x3, you might come back here and write x1, x2, x3. Then we just read out the rows. Row 1 is saying x1, skip all the way to here, is 3. On row 2, there's a 0, so we ignore it. 1 times x2, so just x2 is 1. So write in x2 equals 1. And for the last row, it says 1 times x3 equals -2. So it's just x3 equals -2. So that's our unique solution, and that means the system is consistent. So any questions, folks, with this answer down here? Okay, so that's the method of solving a system. And this is a pretty big system to solve by hand. Without doing it with this matrix process, this could have been an all-class kind of problem, just really working it out, backtracking with silly mistakes and that kind of stuff. Yeah, go ahead.
So, give an example of an answer that we received that would made it inconsistent.
Yeah, absolutely. That's going to be our next problem down below. And also the instructions change a little bit. Here, you're told to solve the system. We identify the pivots, follow the yellow. We had to eliminate entries above and below every single pivot. So once we got here, that's when we were able to solve the system and determine there was a unique solution. There was now a pivot in every row. But the instructions on this next one are very different. It's asking, determine if the system is consistent or inconsistent. We're not trying to solve it. You could solve it to get an answer, but that's working sometimes more than twice as hard as what you had to do. So let's put extra advice here. If it's just determine if the system is consistent or inconsistent, we eliminate entries. Let me highlight that just to say why we're doing it. Eliminate entries only below the pivots. So that's going to be our method if you see these instructions here. They're not even asking for the solution. They're asking, is there one in the first place? So that's the question of this problem. Well, that also takes us to this statement I copied from the text. What we would like to ask about these systems in linear algebra is first, is there a solution? Is it consistent or inconsistent? And next, if there is a solution, how many are there? Is it unique or are there going to be infinitely many different solutions? We're first focusing on consistent versus inconsistent with this question. We'll start looking at the next question there in the coming sections. Well, let's give this a try. First thing I would want to do personally is take all of this, which is very hard to read and work with, and put it in a matrix. That's where everything is happening, and that's where all that matters is brought in. We'll focus on the part of the system that actually helps us answer this question. But it is a little bit tricky to write this one in. Because note the formatting is a little bit funky on this one. It goes x1, x2, then x2, x3, x4. So we have to be very careful on how we actually write this in. So let's start by just putting in the variables, just to be careful. Putting in any extra structure is going to help a lot for this. We have up to x4. So we want coefficients for x1, x2, x3 through x4 on this particular problem. So that's how it's going to start. Oh, and my bracket is a little too soon. Let me fix that. It's going to be augmented, so let me put that in. And then a bracket. So now let's go down the line. For x1, all we want are the coefficients. In row 1, it's a 1. In row 2, x1 never occurred, so the coefficient is 0 this time. Does that make sense to folks on that entry? Awesome. Then over here, coefficient is a -1. No x1 on the fourth equation, so 0 next. Then just rinse and repeat. Pull all of your x2 coefficients line by line. They go -6, +1 from here, +6 from here, and -1 from here. Let me know if I miscopied anything. It's easy to do with all this stuff we have to write in. Now next, any volunteers for the column that will go in here for x3? Anyone see those coefficients? Yes.
Oh, you want to do the whole thing?
Yeah, go for it.
-4. And 5.
Awesome, thanks. So yeah, that's the coefficients for our x3. And again, it's definitely tricky. I would take, if you're taking this to an augmented matrix, go really slow. You could actually save some time on this problem by making sure all the numbers are perfect. And that's because these numbers are rigged. If I miscopy something, like I put a +1 here, this could turn into a really nasty arithmetic problem out of nowhere. So definitely be careful on the very first steps, copying the problem. Next for x4, we'll go 0 from row 1. Then it goes 1, 5, 4. The dash here tells us the system is augmented, and we pull in everything to the right of the equality, 5, 0, 3, 0. And because our whole job is to determine consistent versus inconsistent, we'll identify the pivots. Here's the first one. But only eliminate entries below, not above. Well, here, that means we eliminate everything on this first one. We need to eliminate that -1. Well, we're about ready to start. Any questions so far, folks, on the setup so far? Okay, this is pretty much always the initial setup. Get away from that, abstract down to just the coefficients. And now we're going to operate on just that matrix. This one is just a one-step row operation. We're going to change that -1 by eliminating it. So row 3 is changing. We'll take row 3, replace it with itself, plus row 1. We're simply taking row 1, adding to that entry to get the 0. That means row 1 and row 2 are not changing. Let's copy them in. By rows, it's 1, -6, 0, 0, 5. Row 2 is 0, 1, -4, 1, 0. Here's our operation, just taking row 1, adding it to row 2 to get 0. 0 on this one. 1 on this one. 5. We're adding row 1 to row 2, so the last one will be 8. We've got it. Now, no change on this one. We'll copy it in just as it is. 0, -1. 5, 4, and 0. So just about there, folks. I'm also watching the clock as we go. We won't finish these notes. I have an extra question on here I did want to solve. So I will be moving the due date of the assignment further out, so we have ample time to complete the notes and do the assignment right after. Well, any questions, folks, with that first row operation? Okay. After the operation, we identify the pivots. Pivots in column 1, we're all set. We go down and right. And in column 2, we just need to eliminate that entry below. We don't care about the -6 this time because we're not going for a solution. We're just trying to see if one even exists. So let's eliminate that below. Here's our row operation. We're going to say row 4 is replaced with row 4. And let me take another look at it. Just add row 2 to it. That will work out as well, plus row 2. Okay, so we're only changing row 4. And that means I'm copying in rows 1, 2, and 3. Lots of copying on this one. 1, -6, 0, 0, 5. 0, 1, -4, 1, 0. 0, 0, 1, 5, 8. Now we're ready for our operation. Take row 2, add it to row 3, and we are going to start by that 0. The 1 plus -1 gives us a 0 here. Here we'll get a +1. This one's going to be a 5. And here we'll get an 8. So that's our system so far. Again, analyze the pivots. There's one here, here, and here. This tells us what the next operation should be. Eliminate that entry right there. Yeah, go ahead. Oh, on this one right here? Oh, thanks for spotting that. Yeah, I just weirdly miscopied it in. So that should be a 0. Oh yeah, I was adding that to that. That was a weird error. Thanks for spotting that. Other questions so far on this one?
So we're just trying to figure out consistent and consistent. That's our first solution. We only need to go from 0 below what we're solving for.
Exactly, yes. So what we're going for here is considered to be, if we only eliminate entries below, this will be called an echelon form. And an echelon form turns out to be the right format of your augmented matrix to tell you right away if there's a solution and how many solutions there will be. You just need echelon form. Echelon form doesn't give you the solution, though. That's the trouble of it. If you want an actual solution, like in this problem, then what you're getting here is, this one is called reduced row echelon form. Because we eliminated the entries above the pivots as well, that made it reduced form. But here, we're just settling for echelon. That's good enough for us on this one. Does that make sense, the reason why? Okay, and that's really helpful because, again, that's saving you a lot of operations potentially, spotting the difference in the instructions right here. So last thing we have to do, eliminate that one there. So here's our row equivalent step, and we'll say row 4 will be replaced with row 4 minus row 3. Or in other words, take -1 times row 3, add it to all the entries below. First thing we want to do is tedious though. Rows 1, 2, and 3 just copy in. So once again, 1, -6, 0, 0, 5. Row 2 is 0, 1, -4, 1, 0, and then 0, 0, 1, 5, 8. Finally, the operation starts. Take -1 times row 1, add to row 2, and we'll get 0, 0, and then right here's a 0. -5 plus 5 gives us 0 as well. The -8 plus 0 will give us a -8 right here. Our operation stops right here. Oh, and that's the wrong spot for augmenting. It's augmented, so we'll put this back in. And here, once again, is the variables: x1, x2, x3, x4. Now, this system turns out to be inconsistent. Can anyone see why by analyzing this echelon form? Sorry, say again.
Or is, the last zero is zero, or?
Yeah, it's pretty much this right here. This is a statement that says 0 equals -8. That's a contradiction. Which means the system is inconsistent. Let me try to fix that penmanship. I think I'm trying to beat the 645 on this. The system is inconsistent. Meaning there's no solutions at all to this thing. If you attempt to try to get one, you have to deal with a contradiction. 0 is not -8. And so that's the end on this one right here. Sorry for running right up to the minute. I was going to say, any questions on this one, folks, before we call it a night? Okay. Really, the bigger takeaways on this class is getting fluent with row operation and going from a system to the augmented matrix and vice versa. We'll focus a lot on these row operations, echelon form, reduced row echelon form in the next section. This one's mainly kind of just a preview. Well, this is where we'll end the notes. Let me save this right here. And when we come back, we're going to pick up right on example 6 below. Then we'll move over to section 1.2. Any last questions before we call it a night officially, folks? Yeah.
So is this gonna be posted? Because I'll probably try to work on it over the weekend. Just having access to this would be nice.
Yeah, absolutely. Here's kind of how my workflow looks like. I do have a class after this one. And so when I come home, or usually in the morning the next day, I put in the recorded lecture, the recording for our class. It'll go into this playlist. And I upload the notes right here. I put in the solutions. Even if we don't finish it, I put in the solutions we got so far. I usually get all that done before about 11 a.m. So it's my first thing in the morning. Other questions at the moment, folks? Okay, well, have a nice night. Try to drive safe out there. They're telling us, I mean, DoorDash is canceled for 24 hours. That's how you know it's bad. So it's really bad out there. Drive safe, and I'll see you all on Tuesday next week.
Thank you.
Yep, have a good one.
Thank
you.